There is a seismometer in a disused silver mine in the Black Forest in the south of Germany that sits inside a chamber built to be as boring as physics allows. The floor is bedrock. The temperature barely moves across a year. The instrument is shielded from air pressure, from traffic, from the slow flex of the ground under a passing weather front. All of that trouble exists for one reason, so that when the machine writes something down, you can believe it. On the 16th of September, 2023, at 1:15 in the afternoon, Coordinated Universal Time, that instrument recorded a set of waves arriving from the northwest. Nothing unusual in that. Seismometers pick up distant earthquakes several times a day, and a station that good will register a decent quake on the other side of the planet without anyone paying much attention. The waves came in, the pen wobbled, the file grew. Then the signal refused to stop. Not the loud part. The loud part behaved. The sharp arrivals faded the way they always do, over a few minutes, the way a struck object stops making noise. What stayed behind was something else. And it was so strange that people who had spent their whole careers reading these records had to go and look at each other's screens to make sure they were seeing the same thing. It was a single note, one frequency, 10.88 thousandths of a hertz, which is a phrase that does almost nothing for you until you convert it into something a human body understands. 10.88 thousandths of a hertz means one full cycle every 92 seconds. The ground in the Black Forest was rising and sinking, on a rhythm slower than a deep breath, slower than a long sigh. About a minute and a half from one crest to the next, over and over, with the regularity of a metronome that somebody had wound and then walked away from. The motion was tiny. We're talking about a few tenths of a micrometer, which is a few tenths of a millionth of a meter, which in American terms is something like 100,000th of an inch. You couldn't feel it. You couldn't measure it with anything you own. A person standing on that patch of forest floor would have detected nothing at all, ever, for the entire 9 days that followed. And it did go on for 9 days. That's the part that broke the pattern. Earthquakes are messy. They're broadband, which means they arrive carrying a whole spread of frequencies at once, a chord rather than a note, because a fault rupturing through rock is a chaotic thing happening at many scales at the same time. And they're short. The rupture itself lasts seconds. The reverberation that follows lasts minutes to hours in the worst cases, and then the planet settles back down to its normal background hiss, which is mostly ocean waves drumming on continental shelves. This was one clean tone, held for over 200 hours, and it was everywhere. When the records came in, the same 92-second pulse turned up on stations in Alaska, in Kazakhstan, in Hawaii, on the Canary Islands, in Costa Rica, in New Zealand, on instruments sitting on the ice in Antarctica. From the moment it started, the wave front had crossed from the top of the northern hemisphere to the bottom of the southern one in less than an hour, which is simply how fast surface waves travel through the crust, a bit over 2.5 miles per second. Roughly 4,500 stations, when researchers later pulled the archive, carried a version of it out to a distance of 6,000 miles from wherever it began. Here is what turned it from a curiosity into a problem. Every category of thing that shakes the earth leaves a signature, and seismologists spend their lives learning to sort those signatures by eye. An earthquake looks like an earthquake. A nuclear test looks like a nuclear test. And the difference is one of the more consequential distinctions in geophysics. A volcanic tremor has its own character. A big landslide has a shape you learn to recognize, a smeared, cigar-shaped mess without a sharp start. A collapsing ice shelf, a mine failure, a meteor entering the atmosphere, a heavy storm parked over a coastline. All of them have been cataloged, argued over, and filed. This fit none of them, which is how it ended up with a name that reads like a joke, and was, in fact, mostly a joke, though a slightly nervous one. Researchers trading messages on a group chat began calling it a USO. an unidentified seismic object. The suggestions in that chat ranged from the reasonable to the deliberately ridiculous, and the people involved have been cheerfully honest about it since. Somebody floated an unknown submarine volcano. Somebody floated a very large weapons test. Somebody, in the small hours, floated a fjord monster. And one of the Belgian scientists later said out loud that part of the process involved ruling out a slow alien party. You shouldn't take the joking as a sign that nobody was worried. Joking is what a room full of specialists does when the instruments are behaving in a way that the textbooks do not cover. Because underneath the jokes was a real and slightly uncomfortable question. Something on this planet had been putting energy into the crust, in a perfectly regular rhythm, at a single frequency, for more than a week. Whatever it was, it hadn't stopped when everything else stops. It was still going. And nobody could say where it was, what it was, or whether it was going to happen again tomorrow. The location took a while, and when it came blurred. You can locate a signal by comparing when it arrives at stations spread around the world, but that technique has a resolution limit, and the limit depends on the wavelength of what you're measuring. A 92-second surface wave traveling through the crust has a wavelength of roughly 250 miles. You can't pin a source to a precision much finer than the ruler you're using, and this ruler was 250 miles long. So the answer arrived as a smear, rather than a dot, and the smear sat over the east coast of Greenland. That's a region larger than most countries, mostly uninhabited, mostly under ice, and for the great majority of the year effectively unobserved. Nothing about it narrowed the question much, and then a completely separate thread of information showed up, from a completely separate direction, and it had nothing to do with seismology at all. Greenlandic and Danish authorities had received a report. A tsunami had struck a small research and support station on an island in a fjord system in the northeast of the country. The station had been empty at the time. The damage was obvious and the cause was not. Two mysteries, arriving at two different sets of desks, from two different professional worlds. It took a while for anyone to put them next to each other. When they finally did, what came out was a reconstruction so specific that it reads less like a geology paper and more like an air accident investigation, which is the comparison the people who did it used themselves. 68 scientists, 40 institutions, 15 countries. Nearly a year of work, published in the journal Science in September of 2024, tracing a chain of events from a single fracture surface in a mountainside through a wave taller than almost any wave ever documented, into a phenomenon that most people have only ever seen in a bathtub, and out into a signal that 4,500 instruments recorded without a single one of them knowing what they were looking at. The chain runs through one fjord. It's called Dickson Fjord, and almost nobody has ever been there. Before going to the fjord, it's worth spending a few minutes on the instrument because the whole story hangs off a very particular technical limitation. And if you don't understand the limitation, the ending will sound like magic instead of engineering. A seismometer is a mass hanging from a spring inside a case. That is the entire idea. The case is bolted to the ground, so when the ground moves, the case moves with it. The mass, being heavy and suspended, lags behind. The instrument measures the gap between the two, and from that gap, you can reconstruct what the ground did. Modern versions replace the pen and the drum with electronics and a feedback loop that holds the mass still and records how much force it took to hold it. But the principle hasn't changed since the 1880s. The catch is that the spring has an opinion. Every mass on a spring has a natural period, the rhythm it likes to swing at, and an instrument responds beautifully to motions faster than that period, and progressively worse to motions slower than it. If the ground moves very slowly, the mass has time to follow along. The gap never opens, and the machine sees almost nothing. Slow ground motion is, from the instrument's point of view, indistinguishable from no motion at all. 92 seconds is slow. It sits right at the boundary of what a standard broadband seismometer is built to handle. Most of the world's stations use sensors with a natural period of 120 seconds, and a smaller, more expensive group use 360-second sensors, which are the ones you want for this kind of work. Below that boundary, you're leaning on the correction curve instead of on the raw sensitivity of the instrument, and small errors in the correction turn into large errors in the answer. Stephen Hicks, the seismologist at University College London who ended up co-leading the investigation, put the problem plainly. The 90-second oscillation sits right on the limit of what most seismic stations are designed to detect, which means this event was recorded at all because a set of institutions, over decades, spent money on instruments that were better than they strictly needed to be, installed them in vaults and boreholes, and abandoned mines far from roads, maintained them through budget cycles that had nothing to gain from a fjord nobody had heard of, and gave the data away for free. That's not a small point, and I don't want to slide past it. The Global Seismographic Network exists mostly for two reasons: detecting earthquakes and verifying that nations aren't testing nuclear weapons. Neither of those missions cares about a standing wave in East Greenland. The reason the standing wave got recorded is that the network was built to be honest across a wide band instead of being tuned for one purpose, and the data was published openly instead of being sat on. Take away either of those choices, and this event simply never happens, as far as the record is concerned. It occurs, the fjord sloshes for 9 days, and the human species never finds out. Now, the other thing I want to nail down before we go north, because it is in the title, and it is the single most misunderstood part of this whole affair. The Earth did not shake for 9 days. Not the way you are picturing. The phrase that went around the world in September of 2024 was that a tsunami had rung the Earth like a bell, and it's a lovely phrase, and it is wrong in a way that actually matters. A bell rings because you hit it once and then it keeps vibrating on its own at frequencies it chooses, determined by its own shape and stiffness. The planet really can do that. After a truly enormous earthquake, the whole Earth oscillates in what are called normal modes. The Great Quake in Chile in 1960 famously set the planet humming for weeks, and those modes have specific frequencies, most of them below about 5 thousandths of a hertz. 10.88 thousandths of a hertz isn't one of them. The researchers checked. There's no sharp, long-lived normal mode of the Earth sitting anywhere near that frequency, which is a technical detail with a large consequence. If the planet had been oscillating on its own account, there would have been a mode there for it to oscillate in, and there was none. So the planet was being driven. Something out there was pushing on the crust over and over, 92 seconds apart for 9 days, and the crust was doing what any elastic solid does when you push on it repeatedly. It carried the push outward as waves. So the bell was never the Earth. The bell was the fjord. The Earth was the air in the room. And the volume of that sound, measured honestly, is humbling in the other direction. A few tenths of a micrometer at a station 2,000 miles away. Larger closer in, smaller further out. And buried underneath the ordinary background noise at any station that happened to be in a noisy place or pointing the wrong way. If you had stood on the rim of Dickson Fjord itself during those 9 days, with no instruments, you would have seen water. Moving oddly, yes. Sloshing, yes. But you wouldn't have felt the ground do anything at all. Which raises the obvious question, and it's the right question. If the motion was that small, why did anyone care? Because of the duration and the purity. Energy isn't the same thing as amplitude. A signal that's a millionth of an inch tall but perfectly regular for 200 hours is pushing a very large amount of energy into the crust, delivered slowly. And the fact that it stayed on one frequency the entire time means the source wasn't chaotic. Chaotic sources produce chaotic signals. A source that produces one clean tone for 9 days has to be some kind of oscillator with a fixed geometry, something with a natural rhythm set by its own dimensions, like an organ pipe or a wine glass or a swimming pool. That was the real clue, and it was sitting there in plain sight from the first day. Whatever this was, it had a shape, and the shape wasn't changing. The frequency drifted by only a few hundred parts in a million over the first 2 days. And even that drift turned out to have a pattern to it, running on a twice-daily cycle that anyone who has ever looked at a harbor could name in one guess: the tide. Something out there was resonating, and the tide was very slightly retuning it twice a day, the way humidity retunes a guitar left out on a porch, which is a beautiful clue, and also a maddening one, because it meant the source was in contact with the sea, and the northeast coast of Greenland has an extraordinary amount of coastline for a place with almost no people on it. The tide comes back into this story much later, and when it does, it closes one of the last gaps in the case. The method for finding an invisible source is called back projection, and the easiest way to picture it's to run time backwards. You have thousands of stations. Each one recorded the arrival of the same waveform at a slightly different moment, because each one sits at a different distance from wherever the thing happened. Take those arrival times, take the known speed of surface waves through the crust, and mathematically push the energy back the way it came. Where the reconstructed wavefronts converge, that's your source. It's the same logic as watching ripples reach the edges of a pond and working backwards to the point where the stone went in. It works. It also has that resolution limit. And with a signal this slow, the convergence zone came out as a broad patch rather than a point. The team ran the analysis and got East Greenland. Then they ran it again for each subsequent day, because unusually, they could. Most seismic sources exist for seconds, so you get one location and that's that. This one persisted so they could locate it on day 1 and day 3 and day 6 and day 9 and watch whether it moved. It didn't move. 9 days, same patch of coastline, no drift. Whatever was making the sound was bolted to one place. That immediately killed a whole family of explanations. A drifting iceberg was out. A ship was out. Anything atmospheric was out, because weather moves. What remained had to be geographically fixed, in contact with the ocean given the tidal fingerprint, and capable of oscillating cleanly at one frequency for over a week without any obvious source of energy to keep it going. Meanwhile, in a different building, in a different professional world, a much simpler kind of evidence had arrived. On the 17th of September, one day after the signal began, the Danish Joint Arctic Command received a message from a cruise ship called the Ocean Albatross, which was sailing in the fjord system of northeast Greenland. One of the passengers had previously served with the Sirius Patrol, the Danish military dog sled unit that runs the sovereignty patrols across that coast. He knew what the small station on the island of Ella looked like because he had lived in it. And as the ship came past, he could see that it didn't look the way it was supposed to look. That's the detail I keep coming back to in this whole case. The first human being to notice that something enormous had happened in northeast Greenland noticed it because a building was the wrong shape from a distance, and he only knew it was the wrong shape because he had personally been stationed there. Take that one passenger off that one ship on that one week, and the discovery gets delayed by who knows how long. The station was closed for the season. Nobody was due back for months. The Arctic Command investigated. What they found at Ella was a scene that read clearly to anyone who has looked at coastal damage before. Material dragged inland and then dragged back out. Debris lines above the normal high water mark. Structures shifted off their footings. Gear that belonged in a hut now sitting in the water. Everything pointed at a wave, a serious one, and nobody had reported an earthquake. 2 problems then, sitting in 2 separate inboxes. A seismic signal from East Greenland that fit nothing in the catalog. A tsunami in East Greenland with no visible cause. The distance between those 2 facts was 1 phone call, and it took a few days for someone to make it. Once the call happened, the thing that formed was less like a research project and more like a crash investigation team. The comparison isn't mine. The scientists involved use it themselves, and it's accurate down to the working method. In an air accident inquiry, you have a small number of physical traces and a very large number of specialists. And the job is to build a sequence so tight that each step forces the next one. You don't start with a theory. You start with what the instruments recorded, and you keep asking what could have produced exactly that and nothing else. 68 people in the end, 40 institutions across 15 countries, seismologists in Belgium, Germany, France, Britain, the United States, Costa Rica, New Zealand, Italy, Sweden, Indonesia, landslide specialists, tsunami modelers in Norway and Spain, glaciologists, oceanographers from a marine institute in Belgium, somebody from the Greenland National Museum because parts of that coastline hold archaeology, and the archaeology needed checking. A team from the Technical University of Denmark who work on ice sheet mass loss. The lead author was Christian Svenevig, a landslide geologist at the Geological Survey of Denmark and Greenland, which is the agency that would have to answer for this in policy terms if it turned out to be part of a trend. The evidence they had to work with was a peculiar mix of the very expensive and the very ordinary. They had the seismic archive, which is the crown jewel, thousands of stations, decades deep, free to download. They had commercial satellite imagery from Planet Labs, whose small satellites photograph most of the land surface of the Earth every day at a few meters per pixel. That turned out to matter enormously, because it meant they had a clean picture of the slope taken 2 days before it failed, and another one taken 67 minutes after it failed, with the dust cloud still hanging in the air. They had European Space Agency imagery from Sentinel-2 for the wider fjord. They had photographs and an aerial survey flown on the 19th of September by the Danish Navy, and separate photographs taken from the ground by the Sirius Patrol, which is how the run-up lines got measured against features that a satellite couldn't resolve. They had one instrument in the water, a single sensor package in the western part of the fjord that measures conductivity, temperature, and depth, installed by a research group who wanted to detect ice calving off a nearby glacier. It had been recording throughout. It was also, as we will get to, almost perfectly designed to miss the thing everyone wanted to see. And the way it missed, it's one of the more instructive failures in the whole investigation. And they had a high-resolution map of the seafloor inside the fjord, gridded at about 50 feet, which is unusual for anywhere in the Arctic and turned out to be the single most important dataset in the entire study. Without it, the crucial calculation can't be done at all. With it, the case closes. Everything else had to be inferred. Nobody saw the event. There's no footage. There were no witnesses anywhere in that fjord system, and the nearest permanent settlement is a town of about 450 people, some 200 miles down the coast. Whatever happened in Dickson Fjord on the 16th of September happened in front of an audience of exactly nobody, and every single thing we now know about it was reconstructed after the fact from traces. So let's go and look at the place where it happened, because the shape of that fjord isn't background. It is the mechanism. Greenland, or Kalaallit Nunaat, has a shape most Americans carry around slightly wrong, because the map projection everybody grew up with inflates it into a continent. It is enormous, but the useful number isn't its area. The useful number is that almost all of the people live on the west coast, and the entire northeast quadrant of the island is a national park with no towns in it at all. That park is roughly 375,000 square miles, bigger than Texas and Colorado put together. There are research stations and military stations in it, a scattering of huts, a couple of airstrips, and no permanent civilian population whatsoever. The nearest settlement is Idakor Tor Meet, on the south side of Scoresby Sound, a town of around 450 people that regularly turns up on lists of the most isolated inhabited places on the planet, mostly written by people who have never been there. It's a functioning community with a school and a shop and a hunting economy, and it's roughly 200 miles from where this story happens. North of it, the coastline breaks into one of the most spectacular fjord networks in the world. And I distrust that word spectacular because it does a lot of tourist brochure work. What I mean is specific. The fjords here are deep, long, straight-walled, and steep, because they were cut by glaciers grinding along lines of geological weakness over millions of years. And the rock they cut through is old, layered metamorphic material that splits along plains rather than crumbling. The main artery is King Oscar Fjord, which runs for something over 60 miles. Branching from it, through a series of connections, is Dickson Fjord. It was named in 1899 by Alfred Gabriel Nathorst, a Swedish geologist running an expedition up this coast, and he named it after Robert Dickson, a businessman in Gothenburg who had helped pay for the ship. That's the whole story of the name. There's no romance in it. A Swede put a Swedish financier's surname on a Greenlandic fjord because the financier had signed a check, and the name stuck for 125 years until the day the fjord did something that put it in every newspaper on Earth. The fjord itself is about 20 miles long. It runs northwest for a stretch, then makes a distinct turn and heads west-southwest, and at its head it meets the Hissinger Glacier, a wall of ice at the dead end. Along its north shore, another glacier, the Fulak, comes down toward the water. The land on the north side is called Suessland. The ground to the southwest is called Gletscherland, which is exactly as literal as it sounds. Mountains crowd the whole thing. The highest nearby peak runs to about 7,200 feet, and the walls come down to the waterline at angles that make landing a boat a matter of finding the one place where you can. 3 numbers about this fjord end up doing all the work later, so I will give them to you now and let them sit. It's about 1 2/3 miles across at the place where the mountain came down. It is roughly 1,770 feet deep there, which is 1/3 of a mile of water underneath you, in a channel narrow enough that you could see individual boulders on the far shore. And along that central stretch, the 2 walls run very nearly parallel to one another. That last one sounds like the least interesting fact of the 3. It's the most important. Parallel walls, a fixed width, a fixed depth. That is the specification for a resonator. It's what makes an organ pipe, rather than a hole. But we're getting ahead of ourselves. Human presence in these fjords is thin, and it's old, and it isn't the same thing as emptiness. Along the shorelines, there are archaeological sites from the Thule culture, the ancestors of today's Inuit, who moved east and north across the Arctic roughly 800 years ago and lived on these coasts using the sea ice as a road. There are also huts from the 20th century put up by Norwegian and Danish trappers who wintered here to take fox and bear. And a Danish volunteer association called Nanok has spent decades restoring those huts and keeping them weather-tight, partly as heritage and partly because a standing hut in that country is a genuine survival resource for whoever comes past next. The modern presence is mostly military and scientific. The Sirius Patrol is a Danish naval unit that runs long-distance sovereignty patrols along the northeast coast by dog sled, 2 men to a team, out for months at a stretch. Their headquarters sits at Daneborg, further north. They keep a support station on the island of Ella, in the northern part of King Oscar Fjord, and the Nanok organization keeps a station there as well. In the summer, the island sees researchers and the occasional expedition cruise ship. In the winter, it sees the patrols and nothing else. Cruise ships are, in fact, a regular feature now. In the ice-free season, vessels pass on either side of Ella Island roughly weekly. These are small expedition ships, a couple of 100 passengers, the kind that carry zodiacs, and a lecturer, and a stock of parkas. And the northeast Greenland fjords have become a well-established route for them. That's a change from 20 years ago. And it's a change that matters to this story in a way that has nothing to do with tourism and everything to do with arithmetic. Because here is the situation as it stood on the morning of the 16th of September, 2023. In a fjord system the size of a small country, on a coast with essentially no permanent inhabitants, there was a research station standing empty on an island. A scattering of huts that had been standing for a century, a single scientific sensor hanging in the water for an unrelated purpose, and a shipping season that was winding down for the year. And about 3,900 feet above the water, on the south wall of Dickson Fjord, on a mountain the Danish maps call Hvide Stovhorn, which translates roughly to the White Dust Horn, a slab of rock had been slowly running out of reasons to stay where it was. Rock doesn't fail at random. It fails along surfaces that were already there. The bedrock in this part of East Greenland is metamorphic, which means it was cooked and squeezed deep in the crust long enough that its minerals lined up. That alignment is called foliation, and if you have ever split a piece of slate with a chisel and watched it part into clean sheets, you have used it. Foliated rock has a grain. It's strong across the grain and weak along it. And every geologist who looks at a mountainside is asking, before anything else, which way the grain runs and whether it runs out of the hillside or into it. At Hvide Stovhorn, the grain ran the wrong way. The foliation plains dipped westward at about 45 degrees, straight out toward open air, which means that for as long as that mountain has existed in its current shape, a large wedge of it has been sitting on a ramp, held in place by friction and by whatever happened to be piled against the bottom of the ramp. The wedge wasn't small. When the investigators reconstructed it afterwards, from the scar it left and from three-dimensional models built out of overlapping photographs, they came out with a block of rock up to about 500 feet thick, roughly a third of a mile wide, and a bit more than a third of a mile from top to bottom along the slope, something on the order of 25 million cubic meters, which in American units is around 33 million cubic yards. The comparison the researchers themselves reached for was 10,000 Olympic swimming pools, and I've never found that one useful, because nobody can picture 10,000 of anything. A better one, maybe. Imagine a solid cube of rock, a bit under 1,000 feet on every side. One cube, sitting on a 45-degree ramp 3,900 feet above cold water. Now, the ramp. The failure plane, the surface the block eventually slid on, didn't stop at the ground. It kept going down, below where the ground surface used to be, and what was sitting on top of that lower section was ice. There was a small outlet glacier running down a gully on that slope, about 650 feet wide, where the rock hit it, and the toe of the unstable rock mass was, in effect, buried in it. The mechanic, in ordinary terms. Think of a row of books leaning on a shelf. The whole row is stable because there is a bookend at the low end taking the load. Take the bookend away and nothing happens immediately, because friction between the covers holds for a while. Then it does not. The technical word for the bookend is a buttress, and the word for removing it's debuttressing, and it is one of the standard mechanisms by which glaciated mountains fall apart. Ice fills a valley, presses against the walls, and holds them. The ice leaves. The walls, which were only ever marginally stable, discover this at their own pace. So the question becomes, was that glacier leaving? This is where the study stops being a story and becomes a measurement. And it's worth going slowly, because this is the single link in the chain that carries the most weight in the public conversation. And it's also the link that the scientists themselves stated with the most care. Greenland's glaciers have been surveyed from the air and from space for a long time. Photogrammetry from historical aerial surveys, satellite altimetry, digital elevation models built from stereo imagery. Stack those together, and you can build a record of how the surface of a specific glacier has changed in height over decades. For this glacier, the team compiled the change between the 1980s and 2018. Broken down by elevation band, The glacier had thinned. Across the relevant elevations, the surface had dropped by tens of feet, with the largest losses approaching 90 feet. Some of the highest ground had gained a little. The overall picture was unambiguous. Over about 3 decades, the ice that had been packed against the bottom of that unstable wedge had lost a substantial fraction of its thickness, and the lower part of the rock slide's failure plain extended down into exactly that zone. The language in the paper is, we propose that this thinning led to debuttressing of the lower part of the unstable slope, triggering the rock slide. Propose, not demonstrate. That word is doing real work, and I'm not going to sand it off, because the difference between the two is the difference between science and a press release. What's established? The glacier thinned by a measured amount over a measured period. The failure surface ran through the zone the ice used to support. Debuttressing is a documented mechanism that has been implicated in high-latitude and alpine slope failures elsewhere. Those 3 things together make a strong, coherent case. What isn't established and can't be from one event. That this specific block would still be up there in a world that had not warmed. Slopes fail for many reasons, including reasons that predate any human influence at all. Every fjord on that coast exists because ice carved it, and every fjord wall has been shedding rock into the water since the ice retreated at the end of the last glaciation. Rockfall in Greenland isn't new. What is being claimed carefully is preconditioning, that the removal of the ice made this slope more likely to fail than it would otherwise have been, and that the same process is at work on a great many other slopes. There is a supporting piece of evidence for that, and it is quietly the most unsettling thing in the whole study. When the team went back through the satellite archive looking at that specific gully, they found that the 16th of September wasn't the first time. They identified at least 4 earlier landslides out of the same gully, smaller, unremarked, unreported, plus one more that came afterwards. The mountain had been shedding pieces of itself into that fjord for years. Nobody noticed, because there was nobody there to notice. And because a modest rock avalanche in an uninhabited fjord in northeast Greenland isn't an event, it's weather. Which reframes the 16th of September a little. What happened that day wasn't a mountain suddenly deciding to fall. It was the largest installment so far in a process that had already been running in that exact gully for at least the better part of a decade. The installment that arrived at 11:35 in the morning local time was on a different scale from the ones before it. 12:35 and 3 seconds, coordinated universal time. We can be that precise about the start because the rock announced itself. When a mass that large begins to move, the friction between the sliding surfaces generates a hash of high-frequency vibration, and that vibration travels through bedrock at 3 or 4 miles a second. The nearest seismic station, at Itokortormiet, 195 miles away down the coast, started receiving it a little over a minute later. What arrived there over the following few minutes is, to a trained eye, an extremely legible document. There were 2 distinct bands of information in it, and they were telling different parts of the same story. The high-frequency band, from 2 to 10 cycles per second, came in as a long, smeared burst, lasting around 200 seconds with a ragged tail. That is the sound of grinding. Individual pieces of rock colliding with each other and with the ground. Millions of small impacts blurred into a roar. Landslides make that sound, and the character of it changes depending on what the mass is running over, which is why researchers who study these signals can often tell whether a slide crossed bare rock or loose debris or ice. The low-frequency band, running from about 17 to 100 thousandths of a hertz, was much shorter, around 60 seconds, and it came from something completely different. That band records the bulk of the mass accelerating and decelerating, not the grinding of pieces, but the movement of the whole thing as a single lump, When tens of millions of tons of rock speed up in one direction, the planet has to push them. And by Newton's third law, the rock pushes back on the planet with exactly the same force in the opposite direction. That push is what those long-period waves are, which means that if you record those waves at enough stations and you know the geometry, you can invert the problem. You can take the ground motion and solve backwards for the force. And once you have the force as a function of time, you have the acceleration. And once you have the acceleration, you can integrate to get velocity and integrate again to get position. You can, in other words, reconstruct the path of a landslide you never saw from a wiggle recorded 200 miles away by doing to it what a physics student does to a homework problem. So here is what the rock did, according to the machines. It came off the ramp and accelerated hard. Peak acceleration of about 3.5 meters per second squared, which is a third of the pull of gravity, reached roughly 42 seconds into the movement. 10 seconds after that, it hit its top speed, about 105 miles an hour. Somewhere in that first stretch, it met the glacier. The rock came down onto ice that was sitting in a gully between about 2,000 and 3,000 feet of elevation. And it didn't simply slide over it. It shattered it. And then it took a good deal of it along. The estimate is around 2.2 million cubic meters of ice and glacial debris entrained into the moving mass, scraped off the top roughly 40 feet deep. That detail changes everything downstream, and it's worth understanding why. Ice does two things for a rock avalanche, and both of them are bad news for whatever is at the bottom. First, it lubricates. A layer of ice and meltwater under a moving mass cuts basal friction dramatically, so the slide keeps its speed, instead of grinding to a halt, the way a dry rockfall usually does on a gentler section. Second, it adds volume without adding much resistance. You now have a flow that's part rock, part ice, part slush, moving fast, behaving more like a fluid than a pile. The gully it was running down pitched at 30 to 40 degrees, and the mass turned north inside it, funneled by the walls. Channelization is the technical term, and it matters as much as the lubrication. A rock avalanche that spreads out on an open slope loses energy to its own width. One that is squeezed into a chute keeps everything focused and arrives at the bottom as a coherent slug instead of a fan. The total distance from the failure scar to the water, following the path, was at least 1.5 miles. And in the middle of that path, the seismic record shows two abrupt drops in acceleration, which the team labeled simply as the first and the second. The first is where the mass slammed into the west wall of the gully. The second marks the moment the leading edge of the avalanche reached the fjord. Read that again, because it is the part that always gets me. Somebody sat down with a set of squiggles recorded by an instrument 200 miles away in a town where nobody had any idea anything had happened, and extracted from those squiggles the exact moment a wall of rock and ice hit the side of a gully, and then the exact moment its front edge touched salt water. Then they compared the path they had reconstructed from physics against the path visible in the satellite photographs. The two matched. That's what a solved problem looks like. Two completely independent methods, one using light and one using elastic waves, drawing the same line on the same map. There was a witness of a sort, incidentally, though not a human one. The event was violent enough to punch a pressure wave into the atmosphere, and that pressure wave was picked up by infrasound arrays, the low-frequency listening posts that were built to detect nuclear tests and now spend most of their time recording volcanoes, meteors, and rocket launches. Two of them registered it, one in Norway and one in Russia, at a distance of over 2,000 miles. The mass reached the shoreline and kept going. There was a small peninsula there, about 260 feet by 700 feet, a low apron of sediment that had built up where the Gully Glacier met the sea, and which supported the glacier's calving front. In the after photographs, the peninsula is gone. not damaged, absent. The best interpretation is that the impact also triggered a submarine slide in the sediment pile beneath it, which means part of the material that entered the water that day never appears in any of the aerial imagery at all, because it went straight down the underwater slope and out of sight. And then, having fallen 3/4 of a mile, and traveled 1.5 miles and picked up a glacier along the way, the whole thing went into a channel 1/3 of a mile deep and 1.2 miles wide. Water isn't compressible. It had to go somewhere. The word tsunami has been doing double duty in this story. And before we go further, I want to separate the two things it's covering, because they are related the way a slammed door is related to a room that keeps humming afterwards. A tsunami, in the technical sense, is in Samburati Haumi Sintubawam, is any wave generated by the sudden displacement of a body of water. That's the whole definition. It says nothing about size and nothing about the ocean. Most of the famous ones come from earthquakes on subduction zones, where a slab of seafloor jumps upward and lifts the entire water column above it. And those waves are extraordinary for one particular reason. Their wavelength is measured in tens or hundreds of miles, which lets them cross an entire ocean basin without losing much energy at all. In deep water, they're barely a yard high and travel as fast as a jetliner. They only become terrible when they reach a shelving coast and all that length piles up into height. A landslide tsunami is a different animal built from the same physics. Instead of lifting a huge area by a small amount, you drop a concentrated mass into a small area very fast. The water has to move out of the way immediately, and it does so violently and locally. The result is a wave that can be catastrophically tall right next to the impact, and that fades far more quickly with distance because its wavelength is short, and short waves shed energy, which is why the numbers from Dickson Fjord look, on first reading, like a typing error. The initial impact threw water up the opposite side of the fjord to a height of about 650 feet. 650 feet. Take the Washington Monument, put it at the waterline, and the water goes over the top of it with room to spare. That figure is a run-up height, which means the vertical elevation the water reached on the land, measured afterwards from the destruction line, and in this case a large part of it was backsplash, the immediate, chaotic upward throw of water at the point of impact, the same thing that happens in miniature when you drop a rock into a puddle and get a crown of spray. It is the most violent phase and the shortest lived. The waves that spread away from that impact in the first minute or two ran up the fjord walls to about 360 feet. Those are the figures that put this event into a very small category. Waves of that scale in confined water are rare enough that specialists can list the documented cases from memory. The record holder remains Lituya Bay in southeast Alaska in 1958, where an earthquake dropped a mountainside into the head of a narrow inlet and stripped the forest off the opposite slope to more than 1,700 feet of elevation, a scar you can still see in aerial photographs. Dickson Fjord didn't reach that, and the comparison isn't really fair because Lituya's geometry is even tighter. What Dickson Fjord did was reach the same class. Now the part that keeps this honest, and it's the part that usually goes missing when a number like 650 feet gets into a headline. That wave was gone in minutes, local, violent, and finished. It wasn't a wave that crossed the Atlantic, and there was never any prospect of it doing so, because the geometry that made it so tall inside the fjord is exactly the geometry that prevents it from getting out. A wave with a wavelength of a few hundred yards traveling into an open sea spreads its energy over a rapidly expanding front and dies. Every foot of height it gained from confinement, it loses to freedom. The 9 days belong to something else entirely, and we will get to it, because the thing that made this event globally famous started only after the tsunami had finished. What the tsunami left behind, though, is a record you can read off the landscape. And reading it's how the whole event got measured in the first place. When a wave runs up a slope, it does housekeeping. It strips vegetation. It scours soil down to bare rock. It leaves a distinct line where the water stopped. And above that line, everything looks normal, and below that line, everything looks scrubbed. In photographs taken from a ship or a helicopter, that line is often visible from miles away as a change in color, a band of raw rock and mud between the water and the untouched slope. Investigators walked and flew that line around Dickson Fjord and the connecting waterways and mapped it into categories: places where the water reached a couple of feet, places where it reached 10, places where it reached 40, 60, and the small handful of places near the impact where it reached hundreds. That map is the ground truth against which everything else in the study was tested. If your computer simulation says the wave hit 30 feet at a certain headland and the scar on that headland says 4 feet, your simulation is wrong and you go back and fix it. The pattern of that map tells you a lot about how the wave behaved. It falls off fast, enormously fast. Within a few miles of the impact point, the numbers drop from hundreds of feet to tens. Keep going out through the fjord system, and they drop into single figures. By the time you reach the island of Ella, about 45 miles away by water, the wave that arrived was around 13 feet. 13 feet is still a serious wave. It isn't remotely in the same category as 650. And I want that decline understood as clearly as the peak, because both numbers are true, and only one of them tends to get repeated. There was one more feature of the impact that no photograph could show, and it took the ocean sensors to catch it. When that much material enters a fjord at speed, it doesn't only push water. It stirs up the bottom. Sediment that had been lying undisturbed on the seafloor got thrown into suspension and carried out through the fjord system as a cloud. And a sensor 45 miles away recorded the water turning murky, peaking 3 hours after the wave went past, and the whole episode ran on for 6 or 7 hours before the water cleared. 3 hours to the peak. That's how long it took the murk to make the trip. The wave itself had covered the same distance in a fraction of that time, because a wave is a moving disturbance rather than moving water, whereas the mud actually had to travel. Small detail. It is the kind of thing that only shows up when someone leaves an instrument in the water for years for an entirely unrelated reason, which is more or less the theme of this entire investigation. Ella Island sits about 45 miles out from the impact, in the northern part of King Oscar Fjord, at just under 73 degrees north. It is a small place with an outsized role because it's one of the few spots on that coast where you can reliably put people and equipment ashore. There's a hut complex maintained by the Nanook Association, a research base, and a support station belonging to the Sirius Patrol, the Dog Sled Unit. In September, the island is between seasons. The summer researchers have gone. The patrols haven't yet begun their winter routes. On the 16th, the wave arrived there at about 13 feet. 13 feet of water pushing inland doesn't sound dramatic when you have just been told about 650. Stand at the shoreline and look up 13 feet, though, and it is the height of a 2-story building arriving as a moving wall of water with the momentum of a whole fjord behind it. It came up the beach and pushed roughly 260 feet inland before it stopped and drew back, and it took a good deal of the station with it on the way out. The financial estimate afterwards came to somewhere near $200,000 of destroyed infrastructure. That figure is worth pausing on for a second, because it's small by the standards of disasters and enormous by the standards of that coast. $200,000 in Greenland's national park doesn't buy you what it buys in Ohio. Everything there arrives by ship or by aircraft, in a season a few weeks long. And gear that gets swept into a fjord in September is gear that nobody replaces until the following summer at the earliest. Nobody was hurt, because nobody was there. That sentence is doing a lot of quiet work, and I will come back to it. What the wave did elsewhere in the system is harder to price, and in a real sense, harder to replace. Along those shorelines, there are archaeological sites left by the Thule culture the ancestors of the Inuit who live in Greenland today. These aren't ruins in the monumental sense. They're the physical record of people who lived on this coast. The outlines of winter houses dug into the ground, meat caches, tent rings, the remains of the domestic infrastructure of a marine hunting society that spread across the top of North America and Greenland roughly 8 centuries ago, and adapted to conditions that would kill an unprepared modern expedition in a weekend. A great many of those sites sit close to the water, because of course they do. The water was the road and the larder. A number of them lay well within the reach of the wave, and the assessment afterwards was that they were probably destroyed. Nobody has been out to every one of them to check, because checking would mean chartering a vessel and a survey team for a coastline of that size. What the study could say was that they had been inside the inundation zone. There were also trapper huts from the 20th century, put up by men who wintered on this coast to take fox and polar bear, and several of those were inside the reach as well. One of them turns out to be the most important building in this entire story, and it never had a single person in it during the event. At a headland called Cap Headland, there was a trapper hut that had stood for about 100 years. The wave destroyed it. Think about what that fact establishes. Somebody built a hut on that shoreline in the early 20th century, at a height above the water that seemed reasonable, in a place chosen for its access to hunting ground. It then stood there for roughly a century, through every storm, every spring tide, every calving event off the local glaciers, every rock fall into that fjord system across 100 years of Arctic weather. Nothing that happened in that entire span put enough water over it to knock it down. That building was an accidental instrument, and its message is unambiguous. The wave of the 16th of September, 2023 exceeded anything that had reached that stretch of shoreline in 100 years. I find that more persuasive than most of the numbers, and I think it's because it isn't a modeled quantity. It is a hut. It stood, or it didn't stand. There is no uncertainty range on a collapsed building. The word the researchers used, in the careful phrasing of a scientific paper, was that the destruction of the hut demonstrated the historically unprecedented magnitude of the event. That's about as strong as you can put it while remaining strictly within what a single ruined structure can prove, and it is worth noticing that it is a statement about the last 100 years, and not about the last 10,000. There could have been larger waves in these fjords before there was anyone around to build huts. We would have no way to know unless somebody goes looking for the sediment layers such a wave would leave, which is a study that has not been done here. But within the window where human structures existed on that coast, this was the biggest. A last piece of the local picture, and it's a strange one. The sea level gauge inside Dickson Fjord itself, the sensor sitting about 5 miles west of the impact point, recorded a maximum swing of only around 16 inches from the top of the water to the bottom. 16 inches, 5 miles from a 650-foot wave. That isn't an error, and it's not a contradiction, and the explanation for it turns out to be one of the most important technical points in the whole investigation. But it needs the next part of the story first, because to understand why that instrument saw almost nothing, you have to understand what the water in that fjord had started doing. Let me go back to that sentence about nobody being hurt, because a documentary that skates past, it's doing the story a disservice. Expedition cruising in Northeast Greenland is now an established business. In the ice-free window, roughly July into September, ships work their way up this coast on itineraries built around the fjords, the wildlife, and the light. They're not the enormous vessels people picture when they hear the word cruise. 200 passengers is typical, sometimes fewer, with ice-strengthened hulls and inflatable boats for landings. They pass on either side of Ella Island about once a week during the season. On the day the mountain came down, none of them were in those fjords. Ships had been through in the days on either side of it. The season was still running. The margin was days rather than months, and the researchers noted the routes on their maps alongside the run-up heights, because the overlap between the two isn't a comfortable thing to look at. I'm not going to dress that up into a near-miss narrative, because the honest description is simpler and stranger. A wave of that size went through a network of waterways where, in that season, the probability of finding a ship somewhere in the system on any given day is meaningful. On that particular day, the number happened to be 0. What that coastline can actually do in an emergency had been demonstrated, coincidentally, 5 days earlier. On the 11th of September, an expedition ship called the Ocean Explorer ran aground in Alpa Fjord, in the same national park, in the same fjord system with 206 people aboard. She was stuck fast, upright, hull intact, in no immediate danger. And the assessment from the Danish Joint Arctic Command, which is responsible for search and rescue across that entire region, was blunt. There were no assets in the area capable of assisting. 206 people, a modern vessel with a working engine, in a national park inside a NATO member state, and the nearest thing that could pull her off was not close. The first refloat attempt, using the ship's own power on a high tide, failed. A second attempt, with a research vessel belonging to the Greenland Institute of Natural Resources, also failed. She came free on the 14th on another high tide, 3 days after she went aground. Nobody was injured, there was no pollution, and the hull was never breached. As emergencies go, it resolved about as well as it could. Now put the two events side by side. On the 11th, a ship in that fjord system needed help, and the answer was that help was days away. On the 16th, the fjord system produced a wave with a run-up of 650 feet at the source and 13 feet 45 miles out. The reason nobody died in Dickson Fjord on the 16th of September is that nobody was in Dickson Fjord on the 16th of September. It isn't a story about a successful warning or good judgment or a system working. There was no warning, there was no system. There was a slope, a schedule, and a coincidence. The response, once it started, was quick and it was professional. The Arctic Command received the report from the passing ship on the 17th. On the 19th, 3 days after the event, the Danish Navy flew the affected area and produced an aerial photo mosaic of the landslide zone, which is the imagery that a lot of the later reconstruction was built on. The Sirius Patrol photographed the run-up lines on the ground. Somebody stood in that fjord, looked up at a scrubbed stripe of rock hundreds of feet above the waterline, and took a picture with a scale in it. And that picture ended up in a figure in the journal Science a year later. And this is the part I keep turning over. At that point, in the third week of September, the people who had the tsunami didn't know they also had the seismic mystery. And the people who had the seismic mystery didn't know they also had a tsunami. 2 teams. 1 phenomenon. No shared language. The seismologists were looking at a global monochromatic signal and asking what kind of oscillator produces a single tone for a week. The Greenlandic and Danish authorities were looking at a wrecked station and asking what kind of event produces a 13-foot wave with no earthquake. Neither question suggests the other answer. If you had walked into the seismology chat and said the words rock avalanche, everyone would have nodded, because a rock avalanche makes a perfectly ordinary landslide signal, and they had one of those in the record. It explains the first few minutes beautifully. It explains nothing at all about the 9 days. That was the wall the investigation hit, and it's worth stating clearly, because it's the actual intellectual problem at the heart of this case. A landslide lasts about a minute. You can watch it in the seismic record, start to finish, 90 seconds of chaos, and then silence. There is no mechanism by which a mass of rock that has already come to rest at the bottom of a fjord continues to inject energy into the crust at one frequency with metronomic regularity for 216 consecutive hours. The rock was done. Whatever was still ringing, the rock wasn't it. So the team went looking for the thing that was still moving. Before anybody could find the answer, they had to clear away everything the answer wasn't, And the list of candidates in that group chat is worth walking through because each rejection teaches you something about how the planet actually sounds. Start with the obvious one, an earthquake. Ruled out almost immediately, and for 3 reasons stacked on top of each other. Earthquakes are broadband, and this was a single frequency. Earthquakes are impulsive, with a sharp onset and a decaying tail, and this began by emerging out of another signal and then held steady. And earthquakes have aftershocks, dozens or hundreds of smaller ruptures, on the same fault over the following days, which produce a very recognizable pattern of events at the same location. There were none. East Greenland is also not a place where large earthquakes happen. It sits in the middle of a tectonic plate. It sits in a tectonic plate, a long way from any boundary, and it's among the quieter corners of the planet for earthquakes. Volcanic activity next, which is the standard suspect for long-period monochromatic signals, because magma moving through a plumbing system really does produce them. Volcanic tremor can be beautifully harmonic, and there's a small literature on eruptions that made the whole planet hum. The problem is that East Greenland has no active volcanoes. The region had a great deal of volcanism about 55 million years ago, when the North Atlantic was opening and Greenland was tearing away from Europe. And the basalt from that episode makes up whole mountain ranges further south. That was 55 million years ago. Nothing there's currently doing anything. A nuclear test came up, and it isn't a frivolous suggestion because the international monitoring system exists precisely to catch those. And the analysts who work on this data think about it constantly. It fails on the same grounds as the earthquake. An explosion is an impulse. It puts a large amount of energy into the ground in a fraction of a second, and then it's over. Nothing about a bomb produces a metronome running for 9 days. And if somebody had detonated a device in eastern Greenland, that would have been the least interesting part of the news. Something falling out of the sky. Also an impulse. Also over instantly. An iceberg. Big calving events off Greenland's glaciers do produce long-period seismic signals, and glacial earthquakes are a real and well-studied phenomenon, so this one had legs for a while. It dies on the location test. An iceberg drifts. The source of this signal sat in the same spot for 9 days without moving an inch, and a floating object in a fjord system with tides and currents doesn't do that. Weather. The constant background hum of the planet, what seismologists call the microseism, comes from ocean swell interacting with the seafloor and with other swell, and it's by far the loudest thing on most seismic records. But it's broadband. It changes hour by hour as storms develop and move, and it comes from everywhere at once instead of from one fixed point. It's a hiss. This was a tone. Then, there is the possibility that nobody enjoys raising and everybody has to raise. That the signal wasn't real at all. Instruments malfunction. Feedback loops in a broadband seismometer can go unstable and produce oscillations that look exactly like ground motion and have nothing to do with the ground. Timing systems drift. Software introduces artifacts. Any experienced analyst has been fooled at least once by their own equipment. And the first thing you do with an unprecedented observation is suspect your gear. The argument that killed this one is, I think, the most elegant thing in the entire investigation, and it takes about a sentence. The signal didn't arrive everywhere at the same time. It appeared first at stations nearest to East Greenland, then progressively later at stations further away, and when you plot arrival time against distance, the points fall on a straight line whose slope is about 2.5 miles per second. That is the speed of Rayleigh waves in the Earth's crust. It's a physical constant of the planet, known for a century. And no instrument fault in the world can conspire across 4,500 independent machines, made by different manufacturers, owned by different countries, running different software, to reproduce it. A malfunction is local. A wave has a speed. The move out across the network was the proof that something physical had actually happened before anyone had the first idea what. And there was a second, completely independent confirmation that most people never hear about. The signal also showed up on superconducting gravimeters. Those are a different class of instrument altogether. Instead of a mass on a spring, a superconducting gravimeter levitates a small sphere of niobium in a magnetic field, cooled with liquid helium, and measures the current required to hold it steady. That current tracks the local strength of gravity to something like 1 part in a billion. There are only a few dozen of them in the world, in places like Germany, Belgium, and Canada, and they were built to study things like the tides in the solid Earth and the slow redistribution of water mass across continents. They recorded the 92-second oscillation too. Different physics, different sensor, different failure modes, same signal. At that point, the reality of the thing was beyond argument, and the remaining question was purely one of source. So the list, after everything had been crossed off, read like this: fixed in place, in or adjacent to the sea because of the tidal modulation, oscillating at a frequency set by its own dimensions because the tone never wandered, capable of storing enormous energy and releasing it very slowly, not previously described in the scientific literature in any form. Somebody in that chat had to be the first to say the word Seichi. And to be fair to everyone involved, it isn't an obvious leap. Seiches are a footnote in oceanography. They are the sort of thing that turns up in a lecture on harbor design, with a diagram of a rectangular basin and a worked example about Lake Geneva. Nobody had ever proposed one as a seismic source detectable on the far side of the world, for the very good reason that nobody had ever seen one behave like this. It took a wave in an empty fjord to put it on the map. Carry a full mug of coffee across a kitchen, and you have run the experiment. The liquid tilts up one side, comes back, overshoots up the other side, comes back. And if your walking rhythm happens to match the rhythm of the mug, it climbs higher on every pass until it goes over the rim. The oscillation has a period. That period belongs to the mug and the depth of the coffee, and no amount of careful walking changes it. You can only push it or leave it alone. That's a seiche. The word comes from Lake Geneva, from a Swiss-French term for the way the lake surface rocks. And it was studied properly in the late 1800s by a Swiss scientist named Forel, who noticed the water at one end of the lake rising and falling on a schedule with no obvious cause. Any enclosed or half-enclosed body of water can do it. Lake Erie does it hard enough that a strong wind from the southwest can pile several feet of extra water onto Buffalo while Toledo runs dry, and when the wind drops, the whole lake rocks back the other way for hours. Harbors do it. Swimming pools do it during earthquakes, and pool owners hundreds of miles from a quake have looked out of a window to see the water calmly climbing one end and then the other. Two properties define it. First, it's a standing wave. The water isn't traveling anywhere. It's tilting in place, high at one side while low at the other, with a line down the middle where the surface barely moves at all. Second, its period is set by geometry. Wider basin, slower rocking. Deeper basin, faster rocking. Those are the only two ingredients that matter, and the relationship has been written down since the 1820s. Now apply that to a channel 1 2/3 miles across and 1/3 of a mile deep, with walls that run parallel to each other and drop steeply into the water. You get a rocking motion, side to side across the channel, on a period of roughly 1.5 minutes, 10.88 thousandths of a hertz, 92 seconds. When the team ran their tsunami simulation forward, using the high-resolution map of the seafloor, they watched exactly this happen. For the first 5 minutes after the impact, the water is chaotic. Waves smashing against both walls, breaking, throwing spray hundreds of feet up the rock. Then it organizes. Around 5 minutes in, the mess settles into a clean, regular, side-to-side oscillation of the entire central segment of the fjord. With a peak height of about 24 feet, on a period the model put at 87 seconds. The observed seismic signal said 92. That's a 5% difference. In this line of work, a 5% gap between an independent computer model and a physical measurement counts as agreement, and a good one. The researchers traced the gap to the shallow water right at the shoreline, where the seafloor map is least reliable, and demonstrated the point directly. When they reran the simulation using a coarser map, with grid cells about 400 feet across instead of 50, the answer moved much further away to about 80 seconds. The finer the map of the bottom, the closer the model got to what the seismometers had actually heard. So the fjord was the resonator, the tsunami was the strike, and the tone was the fjord's own. Which leaves the question that actually matters. Why did it last 9 days? Seiches are common. Seiches are also short. Lake Erie settles in a day. A harbor seiche is done inside an hour. The ones documented in fjords after previous landslides in Alaska and in West Greenland produced weak, brief signals that were only detectable on instruments within 20 miles. 4 things about Dickson Fjord conspired, and every one of them is geometry. The first is the direction of the impact. The rock came down the gully and entered the water, traveling almost exactly at right angles to the long axis of the fjord, and it entered near the middle of the confined stretch. If you were designing an experiment to excite a cross-channel standing wave, that's precisely how you would do it. Hit it square, hit it centered, and put all your energy into the mode you want. In the Alaskan and West Greenland cases, the slides came in at an angle, which spreads the energy across modes and wastes most of it. The second is the dead end. At the western head of the fjord sits the terminus of a glacier, a wall of ice sitting in the water. Energy running west hits it and comes back. The third is the bend. Going the other way, out toward the open fjord system, the channel makes a sharp turn. Long waves don't corner well. That bend acted as a barrier, reflecting the resonant components back inward, instead of letting them escape into the wider waterways. Both of the independent tsunami models the team ran showed the same thing. The energy stayed in the central segment, with very little leaking out either end. The fourth is depth. 1/3 of a mile of water beneath the oscillation means the moving mass barely interacts with the seafloor, and bottom friction is the main thing that kills a seiche. In a shallow basin, the water drags. Here, it mostly did not. Put those together, and you have a resonator with remarkably low damping, and physicists have a number for that. It is called Q, the quality factor, and it measures how many times a thing oscillates before its energy bleeds away. A car's suspension has a Q of about 1, which is the point of a shock absorber. A guitar string is in the hundreds. A struck wine glass or a good church bell runs into the thousands. Dickson Fjord started at a Q of about 500 and then climbed. Within a few hours, it was oscillating at a Q of around 3,000, and it stayed there. 3,000 puts a body of water a mile and 2/3 across into the same damping class as a bell. It rocked side to side, something like 8,500 times. 24 feet at first, then less, on a rhythm of a minute and a half, through the middle of September, past the equinox, through 9 consecutive Arctic days and nights, in an empty fjord, with the light going and the first ice of the season forming along the edges. And every single one of those 8,500 rocks pushed sideways on the walls of the fjord, and the walls pushed back. A matching frequency is suggestive. It isn't proof, and the team knew it, because plenty of things in nature oscillate at around a minute and a half, and coincidence is a real hazard when you're matching one number against one number. So they went after it from 4 directions and the four arguments are independent of each other in a way that makes the conclusion very hard to escape. This is the heart of the case, so let me lay it out properly. The first line of evidence is direction, and it involves a distinction that seismologists take for granted, and almost nobody else has ever heard of. When energy travels along the surface of the Earth, it does so in two different flavors. Rayleigh waves roll. The ground describes a small vertical ellipse, up and forward and down and back, the way a floating cork behaves under an ocean swell. Love waves shear. The ground slides horizontally from side to side, perpendicular to the direction the wave is traveling, with no vertical motion at all. Every source generates both, but the ratio between them depends on the geometry of the source and on where you're standing relative to it. And a horizontal force, a push sideways at the surface, has a very distinctive fingerprint. Stand in the direction the push points, and you mostly receive Rayleigh waves because the push is aimed along your line of sight and the ground rocks toward and away from you. Stand at right angles to the push, and you mostly receive love waves because now the push is sliding across your line of sight. That is a directional pattern you can go and look for, and the team had thousands of stations to look at. They found it. Stations lying along the long axis of Dickson Fjord, out to a bearing of about 70 degrees and its opposite, recorded predominantly love waves. Stations lying perpendicular to the fjord, out toward a bearing of about 160 degrees, recorded predominantly Rayleigh waves. Plot the stations on a globe, color them by which wave type dominated, and the pattern that emerges is a four-lobed flower whose axes line up with the walls of a fjord in Greenland. Paula Kuhlemeyer, one of the seismologists on the team, described what that means in one sentence: a force oscillating back and forth at 90 degrees to the long axis of Dickson Fjord. Think about what that requires. From the relative strength of two types of ground motion recorded in New Zealand and Costa Rica and Kazakhstan, you can determine the compass bearing along which something was pushing, and that bearing turns out to be the direction across a specific waterway you couldn't find on a map without help. Map. The Earth is a very large machine for reporting on its own internal traffic, provided you know how to read the receipts. The second line of evidence is magnitude, and this is the one that closed it for me. You can take the amplitude of the ground motion at all those stations, correct for distance and for how the Earth attenuates waves, and solve for how hard something would have to be pushing to produce it. The answer came out at about 5 times 10 to the 11th newtons. That's a number without a shape, so let me give it one. The Saturn V, the rocket that carried people to the moon, produced roughly 35 million newtons of thrust at liftoff. The force that had to be acting on the walls of Dickson Fjord at peak was on the order of 14,000 Saturn V's pushing sideways and reversing direction every 46 seconds. Now the check. Forget the seismic data entirely and ask a separate question. If you have a body of water in a channel of these dimensions rocking side to side, how much momentum does it actually transfer to the rock on each swing? That's a mechanics problem you can do with the geometry and the density of seawater. The team did it. A horizontal shifting of the water's center of mass by about 46 feet back and forth along a 6-mile section of the fjord, at that frequency, transfers exactly the momentum required to produce a force of 5 times 10 to the 11th newtons. And the surface wave height corresponding to that shift, given the shape of the basin, works out at about 30 feet. Their tsunami simulation, running on entirely different physics, had predicted 24. 2 calculations. One starts from ground motion recorded on the far side of the planet and works inward. The other starts from a landslide entering a fjord and works outward. They meet in the middle at the same number, and that number is a wave the height of a 3-story building rocking side to side in a channel in Greenland. The third line of evidence is the decay. Anything that oscillates and loses energy has a decay curve, and the shape of that curve is a signature. What made the Dickson Fjord signal odd was that its decay wasn't a simple exponential. It faded fast at first, at a Q of around 500, and then over a few hours the fade slowed down and settled at a Q of around 3,000, and stayed there for the rest of the 9 days. That's a strange curve. It's also, very closely, what the simulated seiche produced, and the likeliest physical reading of it's simple enough. In the first hours, the waves are big enough to break, and breaking waves dump energy fast. Once the amplitude drops below the breaking threshold, that loss mechanism shuts off, and the only thing left taking energy out of the system is friction, which is slow. Fast damping while it's violent, slow damping once it settles. The final step was to test that directly. They took the water elevation over time from the tsunami simulation, at the point in the fjord where the landslide hit, and fed it into a global seismic wave propagation model as the source. Not as an approximation of a source. As the source itself, the raw output of one model becoming the input of another. Then they let the synthetic waves travel through a model Earth to Germany, and compared the result against what the instrument in the old silver mine had actually written down. The envelopes match. Amplitude, radiation pattern, decay, all of it. At that point, the argument is finished. But there was a fourth thing, and it is the one that pleases me most, because nobody needed it, and it settles the question anyway. The fourth thing is the tide, and it comes back exactly where it was left. Remember that the signal was described as monochromatic. A single frequency held steady for 9 days. That was true at the resolution most people were looking at. When the analysts zoomed all the way in, though, the frequency wasn't quite constant. It wobbled. Very slightly, by about 540 parts per million, which means the 92-second period was drifting by a few hundredths of a second one way, and then the other. And the wobble had a schedule. Twice a day. That is the semi-diurnal cycle, which is the fingerprint of the tide, across most of the world's coasts. And once you see it in a dataset, you can stop guessing about what family of thing you're dealing with. Whatever was oscillating was in the sea, and it was being retuned by the tide. The mechanism is a nice piece of physics, and it's worth a minute. The period of a seiche depends on two things: how wide the basin is and how deep it is. Wider makes it slower, deeper makes it faster. Now bring the tide in. When the tide rises in a fjord with sloping walls, the water gets deeper, which should speed the oscillation up. But it also gets wider because the waterline climbs up the sloping sides and the channel is broader at the top than at the bottom, which should slow the oscillation down. The two effects fight. In Dickson Fjord, the widening wins. So at high tide, the fjord's natural period lengthens slightly, and the seismic signal drops a hair in frequency. At low tide, it tightens back up. Twice a day, for as long as anyone could track it, the tone slid down and back like a string that somebody kept nudging. That's the sort of detail that ends arguments. A rock avalanche isn't tidally modulated. A magma chamber isn't tidally modulated in that way. An oscillating body of water in a fjord with sloping walls connected by a chain of channels to the open sea is precisely and unavoidably tidally modulated, and the direction of the shift tells you something about the shape of the basin's cross-section. The case at that point is closed. A landslide, a tsunami, a seiche, a global signal. Every link tested independently and every link holding. So back to the one instrument that was actually there, because a case this clean tends to hide how nearly it went the other way. There was, remember, an instrument in the water the whole time, a sensor package hanging in the western part of Dickson Fjord, measuring conductivity, temperature and depth, telemetering its readings out year-round from a coast with no power grid on it. It was installed by a research group who wanted to catch ice calving off the Hissinger Glacier at the fjord's head. It had been running before the landslide, during the landslide, and through all 9 days of the seiche. it saw essentially nothing. There were two separate reasons, and each one is a lesson. The first is where it was. It sits in the inner fjord, past the bend, and the simulation showed the Seiche energy staying almost entirely in the central segment. At the sensor's position, the modeled signal drops to the ordinary background noise of the instrument within about 5 hours. The oscillation that was audible on the other side of the planet for 9 days was, 4 or 5 miles up the fjord, already below the noise floor of a device sitting directly in the water. The second reason is worse, and it's a mistake that gets made in every field that records anything. The sensor reported once every 15 minutes. The Seiche had a period of 92 seconds. In the gap between two readings, the water rocked back and forth about 10 times. So the instrument caught the surface at a random phase, then at another random phase, then at another, and the sequence of numbers it produced bore no useful relationship to what was actually happening. The technical term is aliasing, and if you have ever watched footage of a car whose wheels appear to be spinning backwards, you've seen it. The camera samples too slowly for the motion, and it invents a pattern that was never there. That's why the gauge 5 miles from a 650-foot wave recorded a swing of 16 inches. Its numbers weren't wrong in the sense of being broken. They were wrong in the sense of being answers to a question nobody asked. I dwell on this because of what it implies about the rest of the planet. There is a real temptation, reading a story like this, to conclude that we have the Earth pretty well instrumented now. Satellites overhead, sensors in the water, seismometers on every continent. And the honest summary of Dickson Fjord runs the other way. The one instrument physically present, floating in the actual water that was doing the actual thing, missed it completely. The event was caught by machines thousands of miles away that were built for a different purpose, and by satellites that happened to be photographing the landscape for commercial reasons, and by a man on a cruise ship who recognized a building. We didn't detect this event because we were watching. We detected it because we were watching for other things, and it was loud enough to show up anyway. There is one obvious response to that, which is that we're simply better instrumented now than we used to be, and an event like this in the 1990s would have passed without a trace. The team checked. That isn't what the archive says. 3 weeks after the first event on the 11th of October, 2023, it happened again. Same location. Same fundamental period. Same 4-lobed radiation pattern lining up with the same fjord walls. About half the amplitude, and it ran for roughly a week instead of 9 days. When the satellite imagery came in, there was a second landslide out of the same gully, delivering roughly half the vertical run-up of the first one. By that point, the team knew exactly what they were looking at, which must have been an unfamiliar sensation after a month of arguing about fjord monsters. The mountain had thrown another piece of itself into the water water had started rocking again, and every seismometer on the planet, with a decent low-frequency response, wrote down the same note. The same note. Precisely the same note, because the note belongs to the fjord and not to the landslide. Change the size of the rock, and you change the volume and the duration. You don't change the pitch. The pitch is a property of a channel, 1 mile and 2/3 wide, and 1/3 of a mile deep, and it will be the same pitch the next time and the time after that, for as long as the fjord keeps that shape. Which raises an obvious thought, and somebody on the team had it. If this fjord has one note, and the note is distinctive, then it should be possible to go backwards through the archive and look for it. So they did. They took the digital seismic record back to 1990. They also took gravimeter data, which is a different kind of instrument that measures minute changes in the local pull of gravity, and happens to be exquisitely sensitive at very long periods, from a station at Alert in the far north of Canada, going back to 1982. Alert is the northernmost permanently staffed settlement in the world, a Canadian Forces station on the top of Ellesmere Island, and it's been quietly recording geophysical data for decades because there's very little else to do with the location. They searched for the fingerprint. a monochromatic, very long period signal at almost exactly the same frequency. They found four more, four separate occasions, spread across the archive, smaller in amplitude and shorter in duration than the 2023 events, but carrying the same tone from the same place. And at least two of them, one in February of 2016 and one in January of 2017, could be matched against satellite imagery, showing a rock and ice avalanche coming out of the same gully. The same gully. The mountain had been doing this for years, and each time the fjord had sung the same note. And each time the note had reached instruments thousands of miles away, and each time it had gone into an archive and sat there, unremarked, because nobody had any reason to go looking for a 92-second hum from a place with no name recognition and no people. Now look at the two dates on those confirmed earlier events, February, January. Those are deep winter in East Greenland. The fjord is frozen. It's sloshed anyway. That's a surprise. And the explanation is more interesting than it first appears. You might picture sea ice as a lid clamped onto the fjord from wall to wall, which would kill an oscillation immediately. Real sea ice in a fjord doesn't work like that. The tide raises and lowers the whole sheet twice a day, and it can't do that if the ice is welded to the shore. So what forms along each shoreline is a zone of tidal cracks, a hinge, a fractured margin that lets the sheet move up and down with the water. The ice floats, the edges flex, and a slow standing wave can rock underneath it, losing surprisingly little energy at the boundary. The damping was slightly higher in the winter cases. It was nowhere near enough to stop the thing, so the picture that emerges is a fjord that has been ringing intermittently for at least a decade, under ice and under open water, with nobody hearing it. And this settles the question of whether we simply have better instruments now than we used to. According to the team's own assessment, the global seismic networks have been sensitive enough to record signals like this for at least 30 years. The capability was there. The data was there. What was missing was the question. Nobody had ever proposed that a body of water in a fjord could act as a long-lived seismic source, so nobody wrote a detection routine for it. So the signals sat in the archive, being nothing. That's worth understanding properly, because it's how a great deal of science actually works. The discovery in September of 2023 came down to somebody being confused enough by a signal to chase it, and then having the luck to be confused in the same month that a station on an island got wrecked by a wave. No new instrument was involved anywhere in it. For the record, monochromatic signals of this kind aren't unheard of. There's a small catalog of them above 1,000th of a hertz, and almost all of them are volcanic. Magma, moving in a plumbing system that resonates, or a colossal explosive eruption that shocks the entire atmosphere into ringing at its own fundamental frequency of about 3.5 thousandths of a hertz, which is what happened when the volcano at Hunga in Tonga went up in January of 2022 and pressure waves circled the globe several times. The Greenland signals sat outside that catalog, slower to decay, wrong radiation pattern, wrong everything. They were a category with one member, and now they have 6. Up to here, the whole case rests on inference. Very good inference, cross-checked from 4 directions, but inference all the same. Nobody had actually seen the Seiche. The whole thing existed as a computer simulation on one side and a set of ground vibrations on the other, meeting in the middle at a set of numbers that agreed. It bothered people. It should. A physical claim about a wave the height of a 3-story building, rocking in a real fjord for 9 days, and the entire evidentiary basis is a model plus a hum. The image arrived later, from an instrument that had been in orbit for exactly 9 months when the mountain came down. The satellite is called SWOT, for Surface Water and Ocean Topography, a joint mission between NASA and the French Space Agency, launched in December of 2022. Its job is to measure the height of water, all water, oceans, lakes, rivers, reservoirs, floodplains. Mapping where water sits is old news. What this mission added is how high the surface of that water stands, to within a few inches, across a swath about 75 miles wide. The reason that is hard, and the reason SWAT is a landmark, comes down to footprint. A conventional radar altimeter looks straight down and measures the round-trip time of a pulse. It works beautifully over open ocean, and it's been transforming physical oceanography since the 1990s. Its problem is that the spot it illuminates on the surface is several miles across. Over the middle of the Pacific, that's fine. Over a fjord 1 2/3 miles wide, the beam is mostly hitting rock, and rock reflects radar very differently from water. So the measurement is garbage. SWAT solves it with interferometry. It carries 2 radar antennas separated by a boom, and by comparing the phase of the signal returning to each one, it reconstructs surface height across a wide strip at a resolution fine enough to work inside a channel with mountains on both sides. As the project scientist Li Luing Fu put it, the footprint of conventional altimeters is simply too large to resolve such a small body of water. This one is not. So in 2024 and 2025, a group at Oxford went back through the SWAT archive to see whether the satellite had happened to pass over Dickson Fjord while the water was rocking. It had. Several times. For the September event, there were 3 usable passes. One about 12 hours after the landslide, one about a day and a half after, and one nearly 5 days after. For the October event, there was one, roughly 12 hours in. Now think about what a single satellite pass can and can't capture. SWAT crosses that fjord in a matter of seconds. The SAICH has a period of 92 seconds, so the satellite doesn't see an oscillation at all. It sees one frozen instant of it, like a photograph of a swing at some random point in its arc. What that photograph shows is a tilt. The image from the 17th of September, taken about half a day after the collapse, shows the water surface on the north side of Dickson Fjord, standing measurably higher than the water on the south side. About 4 feet of difference across a channel less than 2 miles wide compared against a baseline pass from early August when the fjord was doing nothing at all. That is the SAICH. Caught in the act from about 550 miles up as a lopsided fjord. The Oxford team measured that tilt properly, as a slope across the channel, and the September figure came out about 1/3 steeper than the one they measured in October, which is about what you would expect from an event with half the amplitude behind it. Then they did the necessary hard work of ruling out the boring explanations, because a tilted water surface in a fjord can also be produced by tides pushing through a constriction or by a strong wind piling water against one shore. They ran the tidal harmonics statistically, and they pulled the weather records, and neither could account for what they were seeing. Then they combined the satellite snapshots with the seismic record, which is the part I find elegant, because each dataset supplies exactly what the other lacks. The seismometers have superb timing and no idea of absolute size. The satellite has absolute size and almost no timing. Put them together, and you can solve for the thing neither can give you alone. The answer came out at a SAICH about 26 feet tall at the start. That mattered for a specific reason. The various models that had been run in the meantime disagreed with each other about the initial height, and they disagreed badly, with estimates ranging from around 8.5 feet at the low end to nearly 30 at the high end. That's a factor of 3, which is a polite way of saying that nobody knew. The satellite measurement came down firmly on the tall end and closed the gap, 26 feet. A standing wave a bit taller than a 2-story house, rocking side to side across a fjord in a national park with no people in it, 92 seconds a cycle, decaying so slowly that it took 9 days for the sound to drop below what the machines could hear. And I want to name what actually happened there, because it's easy to miss inside the technical detail. a satellite designed to study sea level rise and river discharge, in orbit for 9 months, operating on a fixed schedule set years in advance by orbital mechanics, happened to fly over the right fjord at the right time, 4 times, without anyone asking it to, and its archive turned out to contain the only direct observation of the phenomenon that had confused the entire seismological community. Josh Willis, at NASA's Jet Propulsion Laboratory, put it simply: seeing the shape of the wave was something we could never do before this mission. Which raises a question that hangs over the rest of this story and doesn't have a comfortable answer. How many other things are in those archives? 6 years before Dickson Fjord, on the other side of Greenland, the same physics ran with people in the way. On the 17th of June, 2017, a mountainside failed above Tsunami Fjord, in the Uummannaq Fjord system on the west coast, a couple of 100 miles north of Ilulissat. Published estimates of the volume set in motion run from about 35 to 58 million cubic meters, which on any of those figures is larger than what came off the slope at Dickson. The wave ran up the slopes, near the impact to something close to 300 feet, and it crossed the fjord and ran up the far side to well over 100. About 20 miles down the fjord sat the village of Nuugaatsiaq. Around 100 people lived there, most of them making their living from hunting and fishing, in a settlement with a heliport, a small power station, and a water supply fed by local streams. By the time the water reached them, it was not a towering wall. It came ashore as waves of a few feet that flooded the ground up to roughly 30 feet above sea level, which in a settlement built along a low shoreline is more than enough. Dozens of structures were destroyed or carried into the fjord, including 11 houses. Something close to half the built infrastructure of the settlement was lost. Several people were injured, and 4 people were killed. Nuugaatsiaq was evacuated. So was the nearby settlement of Ilorsuit. Neither has been reoccupied. The residents were relocated south to Uummannaq and to Qarsut, and the assessment of the slope above the fjord was that it remained unstable enough that returning wasn't a reasonable thing to ask of anybody. I want to be careful about how that is described, because there's a way of telling it that turns a Greenlandic community into a data point in an argument about climate. And that's both disrespectful and inaccurate. What happened at Nuugaatsiaq is that a group of families lost 4 of their people and then lost the place they lived permanently and had to rebuild their lives in towns where they were not from. The hunting grounds they knew, the graves of their relatives, the houses their parents built, the specific knowledge of a specific stretch of coast that takes generations to accumulate. All of it's still there, and none of it's accessible, because the mountain above it might come down again. That's the cost of these events when they land where people are. It isn't primarily measured in dollars of infrastructure. Now put Karat and Dickson next to each other, because the comparison is instructive in both directions. The Karat slide was bigger. It killed 4 people, destroyed a community, and reshaped a piece of Greenland's settlement map. It also produced essentially no global seismic signal worth the name. The SAIS it generated was weak and short-lived, detectable only on instruments within about 20 miles, and nobody outside a small circle of specialists ever heard about the seismology of it at all. The Dickson slide was smaller. It hurt no one, wrecked an empty station and some huts, and set the crust of the entire planet vibrating on one note for 9 days. The whole difference is the shape of the container. Karat Fjord at the impact point is about 4 miles wide, more open, and the slide came in at an angle to the fjord's axis. Energy that goes in obliquely into a wide basin spreads itself across a mess of different oscillation modes, and modes that don't fit the basin cleanly die fast. There's nothing to sustain. Dickson Fjord is narrower, deeper, straight-sided, closed at one end by a glacier and effectively closed at the other by a bend, and the rock came in square. All of the energy went into one mode, and that mode had almost nowhere to lose it. Same physics, same coastline, same decade, same country. One event killed people and produced no signal. The other produced a signal that reached Antarctica and killed nobody. If you are looking for a moral in that, I'm not sure there is one beyond this. The danger of these events and their audibility are unrelated properties. We found out about Dickson Fjord because of a geometric accident that had nothing whatsoever to do with how dangerous it was. Had that same slope stood over a wider or more open stretch of water, the same rock would have fallen, the same wave would have run, the station on Ella would have been hit in exactly the same way, and there would have been no 9-day hum, no international team, no paper in science, and nothing for anyone to investigate. The Arctic would simply have had one more unrecorded rockfall. There's a second thing Karat gives us, and it's less comfortable. The slope above New Gatsiak had been unstable before it failed. Studies afterward found evidence of prior movement on that mountainside, and subsequent work in the same fjord has identified further unstable ground with the potential to generate waves larger than the one in 2017. The pattern at Dickson was the same. At least 4 earlier failures out of the same gully, spread over years, before the big one. Which means that in both documented cases, the mountain gave notice. Nobody was reading it, because nobody was there, and because reading it requires somebody to be systematically looking at satellite imagery of thousands of miles of remote coastline for slow, subtle changes in the shape of a slope. That isn't a glamorous job. It's also, on the evidence of these two events, the single most useful thing anyone could be doing along that coast. The opening sentence of the science paper isn't about a fjord or a signal. It reads, "Climate change is increasingly predisposing polar regions to large landslides." That's the claim the whole study is built to support, and it deserves to be examined properly, because it's the part most likely to be either overstated or waved away depending on who is repeating it. There are 3 physical mechanisms in play, and they're separable. The first is the one we have already met: glacial debuttressing. Ice fills a valley and presses on the rock walls. The ice thins or retreats. The support goes. Slopes that were held in place for centuries by the sheer bulk of the glacier beside them are now standing on their own, and some of them aren't able to. The second is permafrost, and it's less intuitive because most people picture permafrost as frozen soil. In a mountain, permafrost is also ice inside the rock. Every joint, every crack, every fracture plane in a high, cold mountainside can be filled with ice, and that ice is structural. It cements the blocks together, and it seals the fractures against water. Warm it up by a degree or two, and the cement softens. The seals leak. Meltwater gets into places it hasn't been in a very long time, and the effective strength of the rock mass drops. You don't need the ice to disappear. You only need it to get warmer, because ice near its melting point is dramatically weaker than ice at 20 below. The third is precipitation. Where and when it rains and snows in the Arctic is changing, and water in fractures is the classic trigger for slope failure everywhere on Earth, including on your local highway cut. Behind all 3 sits a number that gets quoted a lot and is worth taking seriously. The Arctic has been warming at close to 4 times the global average rate. That isn't a projection. It's a measurement over recent decades. And it's the reason the physical processes above are running faster in the far north than anywhere else. Now, the discipline part, none of that lets anybody say that global warming caused the rock slide at Vita Stovhorn on the 16th of September 2023. Single events don't work that way. That slope had a foliation plane dipping the wrong direction long before industrial civilization, and rock has been falling into East Greenland's fjords since the ice retreated at the end of the last glaciation. There's no counterfactual Greenland to check against. What the evidence supports is narrower and, I think, more interesting. A specific glacier was measured to have thinned by a specific amount over a specific period. The failure surface of the slide ran through the ground that glacier used to hold. Debuttressing is an established mechanism. Therefore, this slope was more likely to fail than it would have been with the ice intact, and every other slope in the Arctic sitting above a thinning glacier is in the same position. That's a statement about probabilities across a whole population of slopes. It isn't a statement about this one rock, and the researchers were careful about the difference. There's a further complication that I have not seen discussed much, and that cuts against the simplest version of the story. We're also detecting more of these events than we used to because there are more satellites, better archives, more people looking, and, since 2024, a specific reason to look. Some of the apparent increase in Arctic landslides is real, and some of it is improved observation. And disentangling those two is very hard indeed. The 4 earlier events found in the Dickson Fjord record are a perfect example. They happened, they were recorded, and nobody counted them until somebody knew what to count. Any trend you calculate from a record like that has to account for the fact that the record itself was getting better. So the honest position is that the mechanism is established, the direction is clear, and the rate of change is harder to pin down than the headlines suggest. Which brings this uncomfortably close to home, because the United States has one of these. About 30 miles northeast of Whittier, Alaska, at the head of Prince William Sound, there's a fjord called Barry Arm. Above it sits a slope containing something on the order of 455 million cubic meters of rock, which is roughly 18 times the volume of what came off the mountain at Dickson Fjord. Historic photographs show that slope has been creeping downhill since at least the 1930s, and the glacier that used to buttress its toe has retreated substantially over the same period. That situation was identified in 2020, and it prompted the construction of one of the most heavily instrumented slope monitoring programs in Alaska: satellite radar to detect millimeters of movement, seismic sensors, infrasound arrays, and an assessment process that runs continuously. The current reading from that program is reassuring rather than alarming, and I'm going to state it in the terms the geologists use, not the terms a headline would prefer. The slope currently shows no sign of large-scale active deformation. Recent modeling suggests that a tsunami generated there would likely be less severe than early estimates feared. Smaller instabilities on the surface still pose a localized hazard. The situation is being watched closely by people who will say so if it changes. A survey of the wider sound found 43 places where landslides occurred between 2016 and 2022, and judged 11 of them capable of generating a tsunami. That's what informed vigilance looks like, and it exists in Prince William Sound because there are towns and boats and a cruise ship terminal there, and because somebody funded it. There's nothing remotely comparable along the fjords of northeast Greenland. So what would you actually build if you wanted to see the next one coming? The study ends with a short list of recommendations, and they're notably unglamorous. No new satellites, no breakthroughs. Just 3 pieces of infrastructure that mostly don't exist. The first is sea level gauges that sample fast. This follows directly from the failure we looked at earlier. There was an instrument in Dickson Fjord, and it reported every 15 minutes, which for a 92-second oscillation is worse than useless because it produces numbers that look like data. The recommendation is for networks of high-rate gauges installed in confined basins across a range of geographic settings, so that when one of these happens, the water itself gets recorded directly rather than being reconstructed from ground vibrations 1,000 miles away. A gauge that samples every second instead of every 15 minutes isn't expensive. The expensive part is getting it to a fjord in northeast Greenland, keeping it powered through a polar winter, and getting the data off it. And those problems are logistical, not scientific, which is a polite way of saying they come down to whether anyone will pay. The second is maps of the seafloor. I said earlier that the fine bathymetry inside Dickson Fjord was the single most important dataset in the entire investigation, and I meant it literally. Without a seafloor map at about 50-foot resolution, the SAISH simulation can't resolve the shape of the basin. The eigenfrequency comes out wrong, and the match with the seismic signal never happens. The team demonstrated that by rerunning the model on a coarser map and watching the answer drift away. Now consider that most Arctic fjords have never been surveyed at anything approaching that resolution. Large stretches of that coastline are mapped from scattered ship soundings and interpolation. So the general problem, which the paper states plainly, is that accurate tsunami modeling anywhere depends on data that's usually missing precisely where these events happen. The third piece is the one with the most immediate practical value, and it comes out of seismology. When a slope fails, two signals leave the scene. One is the seismic wave, traveling through rock at somewhere between 2 and 4 miles per second. The other is the water wave, traveling at a speed set by the depth of the fjord, which in deep water works out at somewhere around 150 miles an hour. Those speeds differ by a factor of roughly 40 to 50, which means a seismometer 60 miles away knows that a large landslide has occurred roughly 20 to 30 seconds after it starts. The wave reaching a settlement at a similar distance takes something on the order of 20 minutes. The gap between those two numbers is the warning, and it exists as a matter of physics, whether or not anyone has built the system to use it. Seismic data also has a property that oceanographic data usually lacks. It's sampled hundreds of times per second, and it's telemetered in real time. Because the earthquake and nuclear monitoring communities have spent decades building exactly that pipeline. The raw capability is already installed. What's missing is the piece of software that recognizes a landslide signature coming from a fjord and does something about it. That is a solvable problem. Landslide seismic signals have a distinctive shape, and there are research groups working on automated detection right now. It wouldn't be a general tsunami warning system in the way the Pacific has one, because that system is built for earthquakes, and its physics assumes hours of travel time. This would be something faster and cruder, aimed at a hazard measured in minutes. And here I have to be honest about the limits of the whole idea, because there is a version of this ending that sounds triumphant and doesn't survive contact with the geography. A warning is only worth what the response is worth. Along the fjords of northeast Greenland, there's nobody to warn. No settlements, no roads, no high ground with a shelter on it. The people who would benefit are on ships, and the options open to a vessel in a narrow fjord with 20 minutes of notice are narrow. What the right move would be depends on the ship, the depth under her keel, and where in the fjord she happens to be, and that is a question for mariners and for the authorities who write guidance for them, not for somebody narrating. In the fjords of West Greenland, where communities do exist, and where Nuugaatsiaq stood, the calculus is different, and the case is much stronger. The mapping work is where the real progress has been. Greenland's Geological Survey has been building a systematic inventory of landslides across the country, using time series of high-resolution elevation models to catch the slow deformation that precedes a collapse. That's the technique that would have flagged Barry Arm in Alaska decades earlier if it had existed. And it's the technique most likely to flag the next Dickson Fjord, before it becomes a Dickson Fjord. It's unglamorous, cumulative work, done by a small number of people with, to my eye, nothing like the resources it warrants. And it's the only approach on the table that puts a warning ahead of the event rather than behind it. There is also a properly new scientific idea sitting in this study, and it has nothing to do with hazard. A fjord has a natural frequency. That frequency is set by its width and its depth, and it changes if the fjord changes, if sediment builds up, if a glacier at its head advances or retreats, if the water column warms or freshens. We now know that when something rings a fjord, the note travels around the entire planet and lands in an archive, which means the seismic record contains, in principle, a set of measurements of the geometry of remote bodies of water, taken by accident, going back decades. Nobody has gone looking for that yet. Somebody will. Picture the fjord through those 9 days, because nobody did at the time, and it's the last thing in this story that deserves to be looked at properly. The 16th of September at 73 degrees north gives you about 12 hours of daylight, and it's dropping fast, losing something like 15 minutes a day as the equinox comes on. The water temperature is a few degrees above freezing. There's old ice drifting in the fjord from the glacier at the head, and along the shorelines, the first thin skin of the season is starting to form and break and form again. On the afternoon of the 16th, all of that gets rearranged. The rock comes down, the water goes up 650 feet, and for about 5 minutes, the fjord is chaos. Then it organizes and settles into a rhythm. North side up, south side down. 92 seconds. South side up, north side down. 92 seconds. 26 feet of tilt at the start, then 24, then 20, dropping so gradually that on any given day you'd swear it wasn't dropping at all. Through the 17th, through the 18th. Past the equinox on the 22nd, when the day and the night balance. And then, the night starts winning for good. Through cloud and clear sky, through whatever weather came across, through the tide coming in and going out and retuning the whole thing by a few hundredths of a second twice a day. By the 25th, the water in Dickson Fjord had gone up and down something like 8,500 times. And the seismometers stopped being able to pick it out from the background noise of the planet. It hadn't stopped. It had only got quiet enough to hide. There's no reason to think the oscillation ended on day 9. Day 9 is when it dropped below what we can hear. That's a fact about our instruments. It probably kept rocking for a good while after that, gently, in the dark, with nobody in the fjord and nobody able to detect it, until friction finally took the last of it. And 3 weeks later, the mountain sent down another piece, and the whole thing started again. Now go back to the room in the Black Forest. The instrument in the old silver mine is still there, still running, still riding down the ordinary traffic of the planet. Earthquakes in Japan, storms in the North Atlantic drumming on the continental shelf, the slow tidal flexing of the crust, the background hiss of a busy world. On the 16th of September, 2023, it wrote down a line that nobody could read. A clean tone, 92 seconds a cycle, a few tenths of a millionth of a meter tall, going on and on for over 200 hours. And for a few weeks, that line was one of the strangest things in geophysics, an unidentified object, a joke on a group chat, a genuine hole in the catalog of everything that shakes the earth. That same line today is a readout. Nothing about it changed. Same frequency, same decay, same four-lobed pattern of love and Rayleigh waves spreading out across the crust. What changed is that we now know it means a mile, and 2/3 of cold water in East Greenland is rocking side to side, which means a mountain called the White Dust Horn has thrown another piece of itself into that fjord, which means a glacier that used to hold that mountain up has thinned enough to stop holding it. An instrument in Germany, reporting on the health of a slope in the Arctic, in a language nobody knew it was speaking. And that's the piece of this I find hardest to shake. The signal was never hidden. It was recorded cleanly by thousands of machines, on every continent, from the first hour. 4 earlier versions of it had been sitting in the archives for years. The information was public and free and complete, and it meant nothing at all until somebody was confused enough to chase it and lucky enough to have a wrecked hut on an island turn up at the same moment. We aren't short of data about this planet. We're short of attention and of the specific kind of stubbornness that makes a person spend a year on a signal that everybody else filed under strange. As for what comes next, the honest version is short. That gully above Dickson Fjord is still active. The glacier below it is still thinning. There's more rock up there sitting on the same set of foliation planes, tipped the same wrong way, and nothing about the situation has improved since 2023. Across the Arctic, there are slopes losing their ice buttresses at a rate we can measure, above fjords we've never surveyed, and some of those fjords have towns on them. We can't say which slope goes next or when. We can say, with real confidence, that the process removing their support is running, and that it's running faster in the far north than anywhere else on Earth. What we have gained is the ability to hear about it. Somewhere, tonight, a mountain above cold water is a little less stable than it was a decade ago. If it goes, the water below it will rock, and the rock around it will carry that rocking outward at 2.5 miles a second, and it will reach a vault in Germany, and a borehole in Kazakhstan, and a hut on the Antarctic ice. And this time somebody will look at the trace and know, within a day, exactly which fjord is singing. One last thing, and it is a narrow question, not a general invitation to comment. Everybody who works with instruments has a signal they couldn't explain. A reading that made no sense, a noise in a dataset, a fault code, a trace on a screen at 3 in the morning, a number that came back wrong 3 times in a row. Machinists, nurses, pilots, radio operators, network engineers, anyone who has ever stared at a gauge and thought that can't be right. Most of the time it turns out to be nothing. Occasionally it turns out to be a fjord in Greenland. Tell me about yours. What did you see and what did you decide it meant before you found out? The ones where somebody chased it and got an answer are my favorite thing to read, and I would like a pile of them. Leave a like if the reconstruction held your attention, and subscribe if this is the kind of thing you want turning up. I make no claims about what a button does. I would simply rather build these for people who actually want them. 92 seconds. 1 note, 9 days. Somebody was listening after all.